So these are geometry problems. You just can't. There's just no way around it. You have to sketch. You have to have good. Even if your sketch is not great, you at least have to have the right image in your mind. Okay, but we want the best sketch that we possibly can. So y equals 2x squared. What is that? Well, that's going to be like this, but then it's going to extend up, right, in the z direction. Something like that. Up and down. And then z equals 0, z equals 7, and y equals 4. Okay, so that should be pretty. So then z equals 0, like that. Y equals 4. I could just make this 4 right here. So this is, say that's 4 right there. And then say that's 7 right there. So first important question was, when you started this, is this what you imagined it was? Did you get this shape? Right? So it's kind of like a, I don't know what that is. It's like a nightstand. Someone I heard. That's a good one, right? So it's like a solid nightstand. It's just all wood, the whole thing, all the way through. $360 nightstand. Okay, so what do we want to do? We want to use a triple integral to find the volume. Okay, so they didn't tell us what to do, A, B, or C, so it's up to us. So what would make the most sense, A, B, or C? So let's talk about A. If we did A, our inner surface would be from what to what? So we always have the surfaces, that's our inner integral, and then our outside double integral, right? So if we do A, we're talking about what to what is our mantra for A? Bottom to top. And then the outside double integral would be? If we do bottom to top, that's the z, that's dz. And then our outside double integral will be the projection into the xy plane. That would be very manageable. That would be, because then in the xy plane, what would we have? We would just have this. So A would be a great choice here. What about B? B would be back to front. How about that? Back to front. It's totally doable. It's just we're gonna have to solve. Let's see. That would be in terms of what? X. And then it's going to be, we'd have to solve this for x, and we'd have square roots involved, right? We'd have a negative opposite of square root for the back and positive square root for the front. So a little less convenience, right? Less convenient, but totally doable, right? That's completely doable. And then actually, then your projection region would be super easy, and YZ, you would just have a rectangle. See that? So that wouldn't be bad. And then what would it be if we did type C, left to right? And so one kind of way to think about this that I didn't talk about is you can think about like an archer. So if it's left to right, then it's like you got an archer over here. And then he's going to shoot an arrow into that thing. And so the left side is where the arrow is going to enter in to the solid, and then the right side is where it's going to leave the solid. So this is especially with what we do today, this may be a helpful thing. So if we're doing type C, then left to right means the archer's over here in negative y territory, shooting into the solid. Into what surface is that thing going to pierce? It's going to be y equals 2x squared, right? And then through what surface is it going to leave the solid? Y equals 4. So if we did, let's go ahead and do that. So then we're going to do type C. So then left is y equals x squared, and the right is y equals 4. So it's going to be dy. Okay, and so then what is our projection region going to look like in that case? going to be from? So we'd have to get these x values. So when y is 4, what, that's that square root of 2? Square root of 2 and negative square root of 2? And then 0 up to, I think this is a rectangle, isn't it? So rectangles and rectangular boxes are easy. We can just, whatever order you want. So I can just do 0 to 7, negative radical 2 to radical 2. And so that would be dy. I did 0 to 7 first, so that would be dz. So I did c1, right? So then the question is, what is our function that we're going to integrate? So this goes to my web work announcement. I made a web work announcement just kind of explaining volume. Yeah, so it's going to be 1. So the reason that works is what you would, it's easier to conceive as a double integral. So in double integrals, if you do the double integral of a surface over a region, then geometrically, what does that find? Finds the net volume of that's between that surface and the xy plane. All right, so if I integrate that fxy over r, double integral over r, from a volume perspective, right, not rate of change accumulation, but from a volume perspective, we would get that volume right there. So what if f of xy were 1? Then what would happen? The amount of volume would be, so that volume would be like area of the base times the height, and that height is 1. So that volume would be the same value as the area of the region. Do you see that? If you have a height of 1, if you have some solid with a height of 1, then the numerical value of the volume is just the same as the numerical value of the area of the base. That should make sense, right? Because volume equals the area of the base times the height. If the height is 1, then those values are equal. So the analogous situation in a triple integral is that if you integrate 1, you're going to get the volume of the thing you're integrating over. Over here, if you integrate 1, you get the area of the region. Here in a triple integral, if you integrate 1, you get the volume of that thing that you're integrating. Okay, so that should be easy to solve. Questions on this example? So if it's some other function of x, y, and z, then from a geometric standpoint, kind of hard to imagine because we're talking about like in 4 dimensions, right? But from rate of change perspective, this would just be some rate of change function, and we're finding the total accumulation across all the ordered triples in our solid, right? So we're letting x, y, and z vary across the solid, and we're getting the net accumulation across that solid at the rate of change of whatever that function is. Okay, questions on number 8? Is it okay? Crystal clear, or you're just totally lost, don't even know what to ask? Some reluctant nods. Okay, can we go on? All right, so we want to talk about more triple integrals, but in some new coordinate systems. So the first is what's called cylindrical coordinates. And it's not really anything too new because cylindrical coordinates is kind of like if you had a triple integral that was type A and then polar. All right, so type A and then polar, that's kind of the idea of what's called cylindrical coordinates. So cylindrical coordinates define points in R3 not as x, y, and z, but as r, theta, and z. Our r and theta are basically our polar coordinates, right? So r is distance from the z-axis parallel to it, out from the z-axis. Theta is our angles, our standard trig angle. The angles measure swept counterclockwise from the x-axis, and then z is up and down. So, for instance, so r is distance out from the z-axis. Theta, standard trig angle. So this is r equals 4.325, and then theta is 2.4 radians, so we're in the second quadrant there. And then say z equals 8.25. So we get a point in space. So this particular point is 4.3, comma, 2.4 radians, comma, 8.25 in z. And that defines a point. So this is an alternate way to define points in 3 space, alternate from x, y, and z, is you use like the polar plane perpendicular to the z-axis and then the height z. So why don't you sketch some points here? Sketch 2 pi over 4, 1. 1 pi 3. And then think about what would this be? Say so sketch points and these equations. So here's the first point, 2 pi over 4, 1. It's in the first octant. R is 2. The angle sweeps halfway through the first octant, and then up z equals 1. And then r equals 1. So 1 pi 3 is in which plane? What plane is that in? What plane is that in? 1 pi 3. Which coordinate plane is that in? XZ plane, right? It's negative x. The x value is negative. It's in the XZ plane. And then the last one. R equals 3. 7 pi over 4 is in which quadrant? Fourth. Like that. And then z equals negative 1. Down below the YZ plane. Oh, I didn't have it. I'm not ready for that. So down below, right? So would that be that point there? Questions on just points, plotting points? Is it okay? All right, so then what would R equals 4 be? R equals 4, how would you describe what R equals 4 is?
Circle, radius, shell, a cylinder.
Okay, I got a circle, I got a shell of a cylinder.
Cylindrical shell.
Cylindrical shell. What kind of, yeah, so what kind of cylindrical shell is it?
It's radius 4.
And how can you,
Centered at the origin.
centered at,
Running along the z-axis.
yeah, so it's the axis, it's a circular cylinder that has the z-axis as its central axis, right? No. So that is using a different R. So how can I want to show that? I want to show that here, and R equals 4 doesn't work because it's interpreting R as something different, as actually just distance from the origin. So what mathematical equation should I put in so we see this thing R equals 4? So what is R in terms of x, y, and z? R equals x squared plus y squared, is that right? R squared, so if I do what? Square root x squared plus y squared, I want that to equal 2 or 4? 4. This is R, right? This is R. Square root of x squared plus y squared is R. And we want R to be 4. Got it. So that's R equals 4 in cylindrical coordinates. Okay, what about z equals 2? So that's easy. How would you describe z equals 2? That's what you should have been thinking, right? Just the horizontal plane. All points in cylindrical coordinates where z equals 2. So it's just going to be all points at a height z equals 2. And then how would you describe theta equals 5 pi over 6? Okay, so a vertical plane. We have to be a little more specific though. Is it second quadrant, right? So is it like the planes that we're used to? Well, how's it different than the planes that we're used to? What's that? Yeah, it kind of has an edge to it, has an end. So it's what we call a half plane. It's a half plane. It doesn't just extend infinitely in all directions. It actually has a boundary, an edge, right? So it's not showing, let's see here if I show more. But anyway, so that's kind of the idea of it. But it's going to look like this. Oh, I didn't like that. Where am I? Very careful here. So if we were, this not gonna work. So if we were to draw that, we wouldn't draw it like a circle like that. We would draw something more like this. Right, so it extends up infinitely, extends out this way infinitely, and down, but there's a true edge here. It's a true end of it, right, because it's only going to point in the direction of 5 pi over 6. So theta equals 5 pi over 6 is what we call a half plane, right? So the z-axis is an edge of it, and then it's going to be all the points like the whole plane that's in the direction of theta 5 pi over 6. Does it make sense?
Mark, why can't it be negative R?
What's that? So yeah, so R is defined as only positive in cylindrical coordinates. So like in polar coordinates, R could be negative,
Right.
but in cylindrical coordinates, R is defined as greater than or equal to 0. Yeah, good question. But right, if R was allowed to be negative, then we would get the whole plane. We would get that whole plane through 5 pi over 6, because R is just defined to be 0 and positive. We get the half plane. Okay, so then triple integrals in cylindrical coordinates would feel pretty similar to, like I said, it's going to feel pretty similar to what? Type A polar. Where you would do, so what would our order of integration be? So triple integrals. No, it's like type A polar. So our function will now be functions of r, theta, and z. And if it were type A polar, then our order of integration would be dz. We're still going to go what? Bottom to top. And then our outside double integral will be like polar. So it'll be r dr d theta. But then the r is going to hook up with the function to be part of the thing that we integrate, right? So that r, we'll get an extra r along with the function, and that will be what we integrate. So just what are relationships? You said r squared equals our relationships between x and y and r, z? X squared plus y squared? X equals r cosine theta, r sine theta, theta equals has to do with tangent, right? Arc tangent of y over x, but now be careful, that has a limited range, right? The range of that will give you an angle, arc tangent will give you an angle between negative pi over 2 and pi over 2. So you have to do whatever adjustments are necessary. If you're, say, in the second quadrant, that's going to take an adjustment. But arc tangent just by itself will always give an angle between negative pi over 2 and pi over 2. So you may have to add pi or subtract from 2 pi or something, whatever you need to get the angle that you need. So these are the same relationships between x and y and the polar plane that we have when we're doing polar stuff. And so then we're going to have our z as some function of, say, r and theta, and that's going to be what? Bottom, right? Bottom to top. And then what's dr? Dr is like outside or inside out, right? Inside, closest to the z-axis, to furthest from the z-axis is our r. And then starting angle is the finishing angle. And it's possible that r could be a function of theta, but usually for our purposes it's not. But that would be possible that these r's could be functions of theta. But the thetas have to be values, right? As you work your way out in these triple integrals, the outside integral has to be just values, because you have no more variables after that to integrate with respect to. So you're going to have to. So z can be a function of r and theta. R could be a function of theta. Theta has to be constant. Anyways, but again, the outside double integral is going to be how your solid projects into the polar plane, or into r and theta, into the xy plane. So again, it's just going to be just like we did, like just a type A polar integral. The difference is that now the surfaces are defined not x, y, z anymore, but they're defined in cylindrical coordinates, which we just talked about, r, theta, z. R, theta, z. Okay, so let's try an example. Okay, so I want to integrate some function f r theta z. And here's the solid. Outside, x squared plus y squared plus z squared equals 1. Inside, x squared plus y squared equals 9. Below, z equals x squared plus y squared plus 3. I should say above, z equals 0. And confined to negative x is less than or equal to y is less than or equal to x. So we're going to need some time to work on this. Again, the artistry doesn't have to be perfect, but it does have to be good enough that you have the right mental image of this solid. Okay, you should. That first thing is what? Sphere. What's the next thing?
Cylinder.
Circular cylinder. Okay. What's the next thing? What's that thing? Z equals x squared plus y squared plus 3? Paraboloid, right? Paraboloid. See how blue looks? Don't worry about it. I'm just making it look good. Okay, don't worry about that. Okay? Yellow instead. That better? Okay, and so then there's one last thing, which is, what does it mean to go from negative x less than or equal to y less than or equal to x?
So it's talking about two lines.
Okay.
Y equals x and y equals negative x.
Yeah, so y equals negative x is where?
The second quadrant.
Nope. Fourth, right? And then y equals x. It's like this. So it's y is greater than or equal to negative x and less than or equal to x. So we're only talking about inside here. Do you see that? All right, so then what will we get? Inside the gray cylinder, above the purple sphere, or outside the purple sphere, and underneath the very dark yellowish paraboloid. So what will that look like? And then confined to this, right? So let's see, I'll outline it. Ready? Here we go. It's going to be like this. And like that. And then like that. Wow, right? Did you get it? Does it make sense? Okay, so what are we going to do? We're going to do cylindrical coordinates, which means Archer is below the xy plane, shooting straight up into the solid. And where is that thing going to pierce out, pierce into the solid from the bottom? Z equals 0. What do you think? Z equals 0? Yeah, it's going to be split up. You see that? So depending on where the Archer shoots into the solid, it's going to be, there's two different bottom surfaces. There's Z equals 0. Oh, I didn't do this. There we go. There's Z equals 0 out here, away from the z-axis, but when you get closer to the z-axis, the bottom is the sphere. What about the top? He said always the paraboloid. Agree with that? Yeah, always the paraboloid. Okay, so we're going to have two triple integrals. And so the first one, let's do this one here. So it's going to be z equals 0 to z equals what? X squared plus y squared plus 3, but we got to change that into cylindrical coordinates. So it'll be r squared plus 3. Okay, and so let's draw the projection plane. The projection plane is from what? Y equals negative x to positive x. And then what do we have? We have this, the place where the sphere is in the inside like this. And then the place where z equals 0 is like this. So there's our projection plane. So when the arrow comes up through z equals 0, which part of the projection are we doing the double integral on? Exhibit A or Exhibit B?
B.
Exhibit B, which means r goes from 1 to 3. And theta goes from negative pi over 4 to pi over 4. Yeah, someone said 7 pi over 4. You could do 7 pi over 4 and then it'd be to 9 pi over 4. But I think this is a little cleaner here. That show up? So there's what? That's the double integral for this part. When the bottom is the z equals 0. Okay, and then gonna have so of what? F times, so we'll just do F times R dz dr d theta, right? Okay, and then the other one. Okay, so z is going to go from the bottom surface is x squared plus y squared equals plus z squared equals 1. So what do we need? We need z as a function of r and theta. So that sphere we need to turn into z as a function of r and theta. So what will it be? Square root of 1 minus r squared. Do you see it? So I would solve for z. It would be 1 minus this, which that's r squared, square root. So the bottom, and now we're doing, what just happened? Actually, I've got a good outline of it, so we'll just leave it, right? So now we're doing this part, right? So my projection now, when I enter into the sphere, I still leave r squared plus 3, right? I still leave at r squared plus 3. And now my double integral will be, r goes from 0 to 1. Theta goes from same angle change, right? And again, f times r times dz dr d theta. And if I wanted the volume of this thing, if I wanted to get the volume of that thing, how would we have the volume? Yeah, so you just f would be 1. And you're going to add these together, right? It's going to add these two triple integrals together. And if you wanted the volume of that shape, then it would be, you just make f1. You still have the r, right? You still have the r's when you're integrating. Questions on this? Very good example. Lots in this. Yes, please?
So why is the radius in the second triple integral 0 to 1 if the shape is outside that sphere?
Because it's the projection into the xy plane. So the projection into the xy plane, it's outside the sphere, but we still take that solid and we flatten it down in the xy plane. And how does that? So how does all that project? So if I So that we're doing this part right here. It's outside the sphere, but then we take that solid and we smash it down, or we shine the light on it, and we get its shadow in the So it's still this. This is the projection, even though it's outside the sphere. There's another hand in the back. So this is bottom to top, right? So what is the top of this thing? It's the paraboloid, right? So this right here is the top of the surface, and that was the paraboloid z equals x squared plus y squared plus 3. So that was one of the surfaces that we were given. It's the top. But we had to write that in terms of r and theta. So x squared plus y squared is r squared. Does it? Yeah. Yeah. So that was just the top surface of this thing. Other questions? Last question, yeah.
I'm still confused as to where the negative pi over 4 comes from. I mean, I know it has to do with it being confined to negative x less than or equal to y, which is less than or equal to x.
Yep.
I don't understand how that translates to that angle.
Yeah, so y equals x, what has rate of change 1? It's that line that splits the first quadrant exactly in half. Well, that's theta equals pi over 4.
Okay.
You see it?
Yeah.
And so same thing, y equals negative x, it splits the fourth quadrant exactly in half in terms of angle. So that's theta equals negative pi over 4. Good? Ask other questions. Okay. So then there's another way to do points in R3. So another system. Can I erase this? And that's called spherical coordinates. Now this is a totally different beast. This is totally new, right? So we have the advantage with cylindrical coordinates of being at least familiar with what we call the type A polar triple integral, and that kind of set the stage. But spherical coordinates is a different thing. It's based on rho, theta, and phi. So two angles, okay? There you go, right?
You heard that right.
Rho, theta, phi. So what is rho? Rho is a version of r, but instead of r like distance from the pole in the xy plane or distance from the z-axis like we saw in cylindrical coordinates, rho is truly distance from the origin in R3. So this is truly distance from the origin. So given any point in space, the value of rho is the distance from that point directly to the origin. Okay? Theta is our same angle that we're used to. Right? It's the angle swept counterclockwise from the positive x-axis. So let's do a point here. So rho is rho is 1.5, and then theta is our same. So it's kind of helps when it's lighter. All right, so this is x here, and this is y here. Everyone see that? Okay, so theta is our standard angle swept counterclockwise from x. So I'm showing that with that like half disk there. So if we did theta equals, here's 5 pi over 4 about, something like that. Then once you pick the angle theta, phi is the angle in the direction of theta tipped down from the z-axis. So watch, here's phi. Now I'm in that direction of 5 pi over 4 into the third quadrant there. Phi is the angle tipped down, yes, from the positive z-axis. So at the xy plane, what would the angle of phi be? Pi over 2, right? Pi over 2. So when you get to the xy plane, it's pi over 2. And then when you keep going, you're eventually going to get back down to the negative z-axis, which will be phi of positive pi. And that's the range of phi. It ranges from 0 to pi. So it's going to tip down in the direction of theta. It's tipping down in the direction of theta from the positive z-axis, so that when it reaches the xy plane, no matter, that's always going to be phi equal to pi over 2, and then it's going to keep tipping down, and the greatest it can be is pi, which ends up being the negative z-axis. Okay, so it's the three coordinates. This is a whole new animal here, right? This is totally foreign. Distance from the origin. Okay, so how far out from the origin? So how far from the origin? 1, 2, 3. So let's make it 1. Here's about 1 from the origin. Theta then is our standard angle. So that's pi over 2, pi, 3 pi over 2, and 2 pi. So here's like pi over 6 or something like that. That's closer to pi over 4. So here's something like pi over 6. Pi over 6 swept, so there's positive x is coming out at you right now. Now here, that's positive y. So this angle is pi over 6. And then phi then is in the direction of theta, tipped down from the positive z-axis. So that it ranges from 0, pointing straight up, pi over 2, horizontal, pi pointing straight down. So this is the point 1.1. Theta is, I tried to do about pi over 6 for theta. And then again, phi is 0. So here's about pi over 4, pi over 2, 3 pi over 4, pi. Okay, so constant values. What would be represented by these? Rho equals 2. Theta equals 2 pi over 3. Phi equals how about also 2 pi over 3. So what would you get from these in spherical coordinates? What would each of these equations give you in spherical coordinates? What set of points would each of those give you? Think about it. Talk about it. Okay, what about rho equals 2?
Spherical shell of radius 2.
All points that are, that's saying all points that are distance 2 from 0, 0, 0 would be a what? Sphere, right? And the radius is?
2.
So then this gives us our first relationship between rho and x, y, and z. What would the relationship then between rho and x, y, and z be if it's rho ends up being what? The radius of a sphere centered at the origin.
X squared plus y squared plus z squared equals rho squared.
He wants x squared plus y squared plus z squared equals?
Rho squared.
Agree? So this is why it's called spherical coordinates, because it's the easiest way to express a sphere. What do you say? If you want a sphere centered at the origin, it's just constant rho. Rho equals whatever radius you have. That's why it's spherical coordinates, because it's based on spheres. Yeah?
Just for sake of clarity, isn't it a spherical shell, not a solid sphere? In this case,
A sphere is only the points distance away. So you don't have to say shell, because that's what a sphere is.
Okay.
So you'd have to qualify that it's a solid by saying like a ball.
Okay.
Solid ball. But a sphere is just all the points that are a distance 2 away, by definition. Okay, are we good on that? All right, what about theta equals 2 pi over 3? All points where theta is 2 pi over 3. Yeah.
Wouldn't it be a half plane with a curved edge?
Same as in cylindrical coordinates, because it's the same angle. So this is a half plane. Half plane in the direction 2 pi over 3. Okay, what about phi equals 2 pi over 3?
It's a cone.
He said cone. What do you think? Is that what you're saying?
The angle extends upward.
So what angle is 2 pi over 3? Phi is 2 pi over 3. Where does that kind of point? Yeah, so 2 pi over 3 is going to be something like that. And now you imagine that all distances and in all angles this way. And what would you get? Oh, so it's not. It's a little less than that. That's like 2 pi over 3 now. Yeah, like that. Okay? Now all distances away and all angle theta is going to give. So now imagine rho changing to all values this way and theta changing to all values around. And what would all the points be then? Cone, single cone. Lots of you saying cone. Yeah, that's right. Single cone. So let's just verify that. If I do, phi equals 2 pi over 3. There it is. So that's the cone 2 pi, phi equals 2 pi over 3. Single cone. Okay, so then we got, in order to set up a triple integral on spherical coordinates, we've got some work to do, okay? This is not a simple thing. So what we need to do is we need to get all our relationships between x, y, z, r, theta, rho, and phi. So the way we're going to do that is we're just going to take a point. So I'm going to turn this off. All right. And then let's do a positive phi. Smaller rho. Okay, so here's the point. Rho is 1.3. Theta is about pi over 4. And phi is about pi over 4. Okay? But it doesn't matter. It can be just, this is just representing any there's more room now. Okay, so first let's kind of sketch out what this would be like with x, y, and z. All right, so z is what? So here's our point, which could be defined as x, y, z. Could be defined as rho, theta, phi. Or r, theta, z. So we want to see how all these things play together. So let's kind of sketch out what x, y, and z would be. So the z coordinate of this is, how would you describe the z coordinate of this? Just in general, the z coordinate is always of a point. Yeah, so it's right. It's the distance from the xy plane. This is the z coordinate. X coordinate. Distance from the yz plane. And then y coordinate. So this is x, this is y, and this is z. Okay, how would you draw r in this picture? R, not rho, but r. how would you draw R in this picture? So everyone think to yourself, how would you show what R is? So from where would I draw? From where to show R? Adam, do you know? What's that? Origin to here? What would that be? What would that distance from there to there be? That would actually be rho. Since it's blue, I'll do it in blue. So that's not R, but someone, so there's some hands raised. Yeah.
It would be from the z-axis to z point, like from where it is up on the z-axis.
Here?
Yeah, and then it would be from that to the z-axis.
Okay, good. So it'd be like this. That's a horizontal line. So I could also put it down here, right?
Yes.
Right? R is the distance to the point, from the point to the z-axis. So it could be down there in the xy plane or up there higher. Okay? So now, where would you draw theta? So everyone, where would you show theta in this picture? That's, I'll do angles in red. So this is theta here. Okay? That's also up here. Okay? And then where would we draw phi or phi?
The angle between rho and the xy.
Here, this is phi here. That's what I heard you say. Is that right? Yeah, no, so it's tipped down from z. Yeah, so you have the right idea, but it's going to be tipped down from z. So I'll go back to black for that. So then this triangle right here becomes very important. This one that has rho and r, and then what is from here to here is what? That's also z, right? So we've got this triangle here with rho, r, and z, and phi. So how could we express z in the other coordinates? Z would equal what? So how would I express z in terms of phi? It's not tangent. Rho cosine phi. See it? Z is the adjacent side to the angle phi. How would I express r? Rho sine phi, right? That's the opposite side of phi. What's the relationships of rho, z, and r? Rho. So this is the right angle. This is the right triangle, right? So theta is in the horizontal plane. Theta is not in this triangle. This is a vertical triangle. Theta is a horizontal angle. This is a right angle here. So what could we say? Rho, r, and z. Rho squared equals r squared plus z squared, which makes sense because what is r squared, we could say, is x squared plus y squared. We backed our sphere equation, right? So this is sphere equation. So now the question is, we have a little chunk of little differential, right? What is like a dv, right? A dv in spherical coordinates equals what? So in spherical coordinates, dv equals what? Well, we're going to have to really work hard to use these relationships. So for instance, in cylindrical coordinates, dv is dz r dr d theta, right? In rectangular coordinates, dv is dz dx dy, or in any order, right? Just a rectangular box. So the next question we have to ask is, what is dv in cylindrical coordinates? Hint, it's not d rho, d phi, d theta. It's more complicated than that, because we got angles now, right? A change in angle is not a distance. So we're going to have more stuff like this coming into it. We'll do it at the start of class on Thursday.